Welcome to this lecture on the computational complexity of algorithms. In this lecture, we will apply our knowledge of the end behavior of functions to the analysis of the complexity of algorithms. Now remember that by definition, an algorithm is a precise procedure that solves a whole class of problems, or problem instances rather, and that does so correctly and in a finite amount of time. So for example, an algorithm for the sorting problem is able to sort any array of integers that you give it as input. So every specific array is a problem instance. Now in general, for a given problem, there are several algorithms that solve it. So the question is, which criteria would you use to choose one algorithm over the others? Well, one possible criterion you could use is to pick the algorithm whose pseudocode description is the shortest. Presumably, a shortest algorithm will be fast to implement. Now, that's not a very common criterion. The more common one is to choose the algorithm whose pseudocode is not necessarily the shortest, but rather the easiest to understand. Now the reason is, the easier the algorithm, the more likely you will be able to implement it fast and reduce your debugging time and minimize the number of errors, and therefore maybe increase the safety or reliability of the implementation. Now in this class, we're not going to use any of these criteria. We're going to instead analyze the efficiency of the algorithms. So in particular, we're going to focus on the execution time of the algorithm. So we're going to pick the algorithm that is the most efficient, that is the algorithm with the smallest execution time. So this criterion is called the time complexity of the algorithm. So let's define this concept precisely. The time complexity of an algorithm is the total amount of time that the algorithm needs to solve the problem. In particular, the time complexity is measured as the total execution time or runtime of the algorithm. Now, this aspect of computational complexity of an algorithm is not the only one. Another important one is called the space complexity of the algorithm. That criterion has to do with the amount of memory that the algorithm uses during its execution. So in this course, we are not going to study the space complexity of algorithms. We're not going to use that criterion. Turns out the amount of memory that the algorithm uses is strongly correlated with the data structures that are used in the implementation of the algorithm. So you will study this aspect of computational complexity in your data structures and algorithms courses. Again, in this course, we're going to focus only on one aspect of computational complexity, which is time complexity. Having selected the time complexity as our criterion of choice, we need to dig a little deeper. For example, how actually should we measure the runtime of an algorithm? An obvious answer would be to just use a timer, or look at the clock on the wall and write down, the start time and the end time and just do the difference. Now, if we measure the runtime like this with a timer, what unit would we use to record the runtime? Well, maybe we could take the number of seconds, or maybe the number of minutes or hours, depending on how fast or how slow the algorithm takes. Now, this view is a little bit too simplistic. We should really ask ourselves, what factors affect the runtime of an algorithm? And it turns out that there are many factors besides the algorithm itself. In particular, it's typically not possible to execute the algorithm directly. It must be first translated into a programming language. And this implementation step has a lot of opportunities for external factors to affect the efficiency of the algorithm. So, for example, a given algorithm may run at different speeds when written in a different programming language. or when executed on a different computer. So maybe the runtime of the algorithm measured in seconds is probably not the best measure of the efficiency of the algorithm itself. Maybe it's a good measure of the efficiency of the implementation of the algorithm. But we don't want the same algorithm to have two completely different runtimes simply because it was compiled with a different compiler or just run on a different computer. So it seems that maybe the number of seconds of actual execution is probably not the best way to measure the runtime or the time complexity of an algorithm, because it does not give a good picture of the runtime of the algorithm itself. It might focus a little bit too much on the implementation details and the runtime environment of the computer system. So instead of using an actual measure of the runtime of an implementation of the algorithm, we would like to find a measure of the runtime of the algorithm that is independent of the details of implementation. That is, a measure that is based only on the features of the algorithm itself. So what we're going to do is actually measure the time complexity or the runtime of an algorithm by counting the number of basic operations or primitive operations that the algorithm executes. Now, what's a basic operation or primitive operation? Well, first, it's an operation that any computer can readily execute. Maybe it's a machine instruction, like an integer comparison, or maybe an integer addition, or maybe an assignment statement. Other possible primitive operations include floating point operations, for example. So depending on the algorithm, you will choose what is the best or most appropriate primitive operation to consider, and then you're just going to count how many such operations the algorithm executes. Now, one important feature of a primitive operation or basic operation is that it not only must be executable by the computer, of course, but its execution must take a constant time that is independent from the size of the input. So, for example, if I give you an array with 1,000,000 elements in it, and the sorting algorithm uses integer comparisons to sort that array, while an integer comparison of two integers takes the same amount of time regardless of the size of the array or even the size of the integers. So these operations take constant time. Again, that time does not depend on the size of the input. Now sure, some computers will be able to do comparisons faster than others, but that's an implementation detail. What we want to assess is the time complexity of the algorithm itself. So to compare two algorithms in this scheme, we're going to compare the total number of primitive operations that each algorithm executes. And so the most efficient algorithm will be the one that executes the smallest number of primitive operations. Let's start our study of the time complexity of algorithms with a simple example. Consider the following problem. Given a finite sequence of integers, the problem is to find and return the largest integer in the sequence. Let's use our pseudocode notation to describe a simple algorithm to solve this problem. Remember, we use the function keyword to indicate that the algorithm returns a value. Then comes the name of the algorithm, the list of parameters or inputs. In this case, is a single input, the sequence of integers a sub 0 to a sub n minus 1, so the size of the input is n. And then comes the type of the return value, here an integer, since it's one of the elements in the sequence, the largest one. So the algorithm will use a variable called max, which we will initialize to the first element in the sequence. Max is going to store the largest element found so far, in this case, the first element, which is the only one we have looked at so far. Then we're going to execute a loop over the remaining elements a sub 1 through a sub n minus 1 using the loop variable I, and for each element after a sub 0 we're going to compare it to the current value of max, and if the current element is larger than max, then we replace the old value of max with the value of the current element. Therefore, when we exit the loop, we have looked at all the elements in the sequence. Max contains the largest one of them, and we just return it. Now, the time complexity of this algorithm will be the number of primitive operations that it executes. So let's study this time complexity. And the first question we must answer is, what are the primitive operations contained in this algorithm? Well, the first one is an assignment statement. The next one is a loop. Now remember, a loop in this case is not a primitive operation because its runtime depends on the size of the input, namely the value n. However, the body of the loop contains an integer comparison right here and then another assignment statement right there. Now, the loop itself has an overhead. Notice to execute the loop, you must first execute an assignment statement, and then hidden here are two primitive operations, namely the comparison of I to n minus 1, which is the upper bound, at which point you exit the loop. And there's also an assignment statement to increment the value of I by 1 every time you execute an iteration. So in conclusion, the possible primitive operations are assignment statements and integer comparisons. So we could pick either one of those. Now, which one should we pick? Well, the answer is we should pick the one that is the best representative of the runtime of the algorithm. In other words, maybe the one that's executed the largest number of times. And clearly here, the execution of the loop will drive the runtime of the algorithm. So, how many times is this loop executed? Well, the answer is n minus 1 times. Now, every time you execute the loop, which instructions get executed? Well, besides the one in the loop itself, you have this comparison here and this assignment. Now notice, the comparison here is the only one that gets executed at every single iteration, because if the comparison is false, then the assignment does not get executed during that iteration. So it appears that the comparisons of these two integers, in this case, is the best representative of the runtime of the algorithm. So the answer to the question here is we're going to use as primitive operation the comparisons. So now that we've chosen the type of the primitive operations we're going to count, we actually need to count them to determine the time complexity of this algorithm. So notice for every iteration of the loop, there is first a comparison performed here at the top to make sure that I is less than n minus 1. So that's one comparison here, a second comparison here. So in other words, there are two comparisons for each iteration of the loop. We already observed that the number of iterations of the loop is n minus 1. So therefore, the runtime or the time complexity of the algorithm looks like it's going to be f of n equals 2 times n minus 1. There's two comparisons per iteration and n minus 1 iterations. Now we should be a little bit more precise here. It turns out, what happens at the end of the execution of the loop? Well, the loop is not exited until I actually reaches the value n minus 1, or rather the value n. So in other words, there's one extra comparison at the last iteration to determine that I has grown too large. So let's keep track of this extra comparison in the time complexity of the algorithm. Now, this is the complete expression of the runtime of the algorithm as a function of n, which is the size of the input to the algorithm. Now we can simplify this expression to 2 times n minus 1. and we can use our knowledge of the big O or the big theta notation. Since this function is a polynomial of degree 1, we know that it is big theta of n. In other words, it's a linear function. So this is a really good algorithm because the runtime grows linearly with the size of the input. In other words, if you double the size of the input, you double the runtime or the time complexity of the algorithm. Now, before you conclude your analysis of the time complexity, it's always a good idea to perform a sanity check to make sure everything looks all right. Notice that to find the largest element in a sequence of n elements, the minimum amount of work you have to do is to look at all of them. So the best possible runtime is a linear time, namely f of n should be a function of at least n, and that's exactly what we found. In fact, you might be worried that we are underestimating the runtime here. This might be too good to be true. In particular, notice we never took into account the number of assignment statements. Remember that there's an assignment statement here within the loop to assign the new value of I every time, and there's also an assignment statement here in the body. So in the worst case, we could be doing 2 assignment statements for each iteration of the loop for an additional 2 times n primitive operations. And by the way, there's another assignment statement here. So really, if we counted the number of assignment statements, we might have to add a whole new set of primitive operations, namely 2 times n plus 1 of them. Would that actually change the runtime of the algorithm? Well, sure it would, but maybe not in terms of time complexity. In fact, notice what happens is if you add 2n plus 1 to this quantity, you get basically 4 times n. And 4 times n is still a linear function of the input side. In other words, it does not change the analysis if we took into account the assignment statement. So our choice of the comparison were actually a valid one, and it is the case that this algorithm is of order n. It's a linear time algorithm.